Our previous lecture, in lecture 5, we did cover on this topic, of electric intensity for the case of volume charge distribution. Okay, so as I mentioned in the class last Tuesday, we're not going to cover in detail of this volume charge distribution. So this topic basically will be covered in detail in chapter 3, in which we're going to start the lecture by today. Lecture 3 will be on topics of flux density, and also on the Gauss law. So let us proceed with sample of test 1. So this is what we have. I've given you this slide in the in Google Classroom. So let us proceed with the sample of test 1. The first question is related to topics that we have learned previously. So we are given a plane of z equals to 5 meters, which carries a charge of 20 nanocoulomb per meter squared. Okay, and a line of x equals to negative 10, z equals to 0 meters, carries charge of 5 nanocoulomb per meter. So in this particular questions, we are given two types of charge distribution. The first one is a surface charge density. So this is a rho s. Secondly is a line charge density, which is a rho l. Okay, so the question is to find the force exerted on a point charge q, which is 15 nanocoulomb located at the origin. Okay, so we can sketch the problem to be look like this. Okay, so we have this should be your z-axis. Okay, so that should be your x-axis, and that should be your y-axis. So let us proceed with the sketching of the surface charge distribution first. So it's given that the surface charge distribution is located here on this particular plane of z equals to 5. And the charge on this surface is 20 nanocoulomb per meter squared, which is a surface charge density. Okay, and then we have another charge type. In this case, it is a line charge distribution located at x of negative 10 and z equals to 0 meters. Okay, so where should this particular line charge is located? So basically x negative 10 should be here. Okay, and on this particular line charge, the coordinate of z, the point of z should be having 0 value. So it means that your line charge should be located somehow parallel with the y-axis. So that should be the location of your line charge. So this is a line charge of a 5 nanocoulomb per meter. Okay, so that should be the sketching of your charge distribution. So hopefully you must be able to understand. You must be able to sketch the exact position, the exact location of your charge distribution. Okay, so with this, you need to find the force exerted on a point charge q of 50 nanocoulomb located at the origin. So your point charge is said to be here. Okay, if you can use the red color. So the point charge is located here, which is having charge q of 15 nanocoulomb. Okay, so what you can do now is that you need to understand, that from what we have learned in chapter 2, I mean in the Coulomb's law, that the force and the electric field intensity by right are interrelated. Are interrelated. That's what we have learned previously. Okay, so it can be said that the equation that shall be used in solving this problem will be F, which is the force, will be equals to charge Q multiplied with the electric field total. Okay, that should be the case. Okay, in which the electric field total, right, should be the total electric field produced by both surface charge structure and the line charge structure. Okay, and we can simply write that the E total can be further written to be the E field, which is produced by the surface produced by the surface, Okay, I put it here, surface charge, yeah, just a surface, plus the E field which is produced by the line. Okay, yeah, so that should be um, should be how the total electric field is actually obtained. Yeah. Okay, so E field produced on this particular point, yeah, because we have the location of the surface charge is at z equals to 5. Yeah. So from what we have learned previously, that due to the case of infinite area of surface charge, yeah, because we are not given any conditions on the area of the surface charge. So we can assume that the surface charge is infinite in area. So as such, we can simply use the equation of rho s over 2 epsilon naught of a normal unit vector direction. Okay, so this is what we have learned previously, yeah, in Coulomb's law. Okay, so we have these epsilon naught terms. Okay, and for the E field due to line charge, yeah, this is your line charge. Okay, so the E field produced by the line charge to this particular charge of 15 nanocoulomb should be written as rho L divided by 2 pi epsilon naught of R direction of R. Yeah, because in this particular case, the line is assumed to be infinite in length. Yeah, so as what we have learned for the E field due to infinite length of line charge, the E field equation should be written like this. Okay, right. So we can simply substitute the respective normal unit vector and the unit vector of R and also the distance of R with respect to the given or with respect to the obtained sketch diagram here. So we can write that the rho s should be equals to 20 nanocoulomb. So I just put 20 nano here over 2 epsilon naught. And normal should be direction of normal from this surface charge that we have here to this particular point of Q, in which the normal unit vector by right shall be equals to negative of z, yeah? Okay, so we're going to put it here as negative of z direction. That should be your normal unit vector. And for the rho L, we're going to have it given here will be 5 nanocoulomb. It's 5 nano only. So we have 2 pi epsilon naught. Okay, remember the equation for this infinite length of line charge where r is a radial distance, yeah, from the line charge to the point of interest. So we can see that this should be your radial distance, okay, in which the distance is should be equal to 10, yeah. So that should be the distance of r, yeah, from line charge to the point of interest. So your r here shall be equal to 10. Okay, so I hope you understand why we use 10 here as r value. Okay, and for the unit vector of r, so clearly shown from this diagram that unit vector of r from this particular point to this point of interest should be in the direction of positive x, yeah, direction of positive x. So that should be the direction of unit vector of r. So we're going to have it as unit vector of x. Okay, so that should be how you obtain the E total. Yeah, the E total or the total electric field produced by both surface charge and the line charge to the point here. Yeah, to the point here at the origin. Okay, so once we have the total electric field, so please calculate this on your own. You're going to have the value in volt per meter unit. Okay, and subsequently, you can use this E total to find the force exerted on the 15 nanocoulomb point charge. We're going to have the F should be equals to 15 nano, a point charge magnitude, multiplied with the E total, which has been obtained previously. So that should be the force produced or force exerted on a point charge of 15 nanocoulomb, which is located at the origin. Okay, so do you understand on how this problem is solved here? Any question for this example? No, yeah? Okay, let us proceed with the next example here. We are given two long parallel conductors of a DC transmission line, which are separated by 2 meters, having charges of rho L of 0.5 microcoulomb per meter of opposite sign. Okay, means that we have two conductors. One is positive and one is negative charge. Okay, both lines are 8 meters above ground. Assume the ground is z equal to 0 plane and the lines are parallel to the x-axis. Okay, so let us sketch these given information. So in EMT, it's very important to sketch the problems. Yeah, so you must be able to sketch the problems, because sketching in EMT will be considered as a mark. Yeah, so you're going to have one or two marks from a sketching process. Yeah, because if you cannot sketch the problems, you cannot solve the rest of the problems. Yeah, so you must be able to sketch. So one or two marks will be given for the sketching effort. Okay. So let us proceed with this. We are given the conductors here. Okay. So we have that should be the x. Sorry, that should be y. Yeah. That should be x axis. Okay, and that should be your z axis. Okay, that should be your z axis. Okay, so it's given that your parallel is said to be separated by 2 meters with a charge of 0.5 microcoulomb per meter of opposite sign. The lines are 8 meters above ground, and assume the ground is at z equal to 0 plane. Okay, so that should be your plane. Yeah, the ground is basically the xy plane, I can say. Yeah, so that should be your ground, which is at the xy plane or z equal to 0 plane. Yeah, the line 2 meters apart. Yeah, so we can see that one of it is located at -1, and then the one is located at +1 of y. Yeah, the locations of both lines are 8 meters above ground. So let's say we have, this is 8 meters, this is also 8 meters, so I can sketch it to be look like this. Yeah, so the line is said or are said to be parallel to the x-axis. So that's how your line chart should looks like. Yeah. Okay, so that should be your line chart structure. Yeah. Okay, so I can need to have, okay, that should be how it should looks like. Yeah, so 8 meters above ground, location is at -1 for y and +1 for the y. So let us assume that one of it is positive and another one is negative. So let us put it here as a positive charge. This is 0.5 microcoulomb per meter, and here it should be a rho L of a negative 0.5 microcoulomb per meter. Okay. Right. Okay, any question for the sketching? Okay,
Doctor,
so that's how we sketch
why
the
you
diagram.
direct?
It,
Doctor,
hello,
why
you have
you
a
direct?
question?
Yeah. Doctor, why you direct assume the rho L for each for the two parallel, for one is negative and one is positive? What is the indicator?
It's yeah, opposite sign, right?
Oh, okay. And the other one is
Okay.
if it direct say separated by 2 meter, we just give it one is -1 and one is 1, or we can give it any 2 meter like 0 and 2.
Any 2 meters should be okay then. Should be no problem.
Okay.
Yeah. Okay. All right. So good question. Thank you very much for your response. Good. At least I know that you are concentrating on my lecture. It's very good. Okay, so let us have a look at part A of the question, which is to find the force per unit length each line exert on the other. In other words, is to find the force that is produced on one force per unit length, yeah? Force per unit length that produced on one line charge due to another line charge. Okay, so that's what meant by question of part A. Okay, so in that particular case, let us assume that we want to find out the force at this particular point, yeah, this particular point on negative rho L charge distribution. Like for example, we assume that that should be the line, I mean the portion of your charge. Let's say we assume that that should be your DL, yeah, a portion of DL, and we know that from what we had learned previously on this particular DL, that should be a charge of dq. Okay, and dq can be written as equals to rho L dl. And knowing that your charge is parallel to the x-axis, so we can simply write that your dl basically should be dx, yeah? So that should be further written to be rho L of dx. Okay, so I'm choosing this particular point dl here, or dq here, such that I want to first find the electric field produced by this line charge of positive rho L to this particular point. Okay, that should be my first aim. Yeah, my first objective is to find the E field. Yeah, find the E field produced by this particular line charge. Yeah, this line charge of positive rho L to this particular point. Okay, so once I have this E field produced at this particular point, then only I can proceed with finding the force. Okay, because from previous example that we did, in order to find the force, you need to find the E field first. Once you have the E field, then you can find the force. Yeah. So similarly, in this particular example, I'm finding the E field first. Okay. So we know that we are dealing with the line charge, which are infinite, yeah, for both cases of positive and negative rho L. Okay, so allow me to use the red color line. Okay, can we use other color then? Not sure whether, okay, the ink color, I'm using the blue color, then easy for me. Blue or green, either one. Okay, let's just screen the color. Okay, so let us, okay, that should be the line chart. So let us, okay, okay, this is the E field, yeah? That should be the E field produced by a positive rho L to this particular point. Okay, we know that this is infinite in length, yeah? So from what we have done previously, the E field, let's say we just write this as a E1, yeah? Just say E1, yeah? So we can see that E1 will be equals to positive rho L, yeah, we have positive rho L, over 2 pi epsilon naught R in the direction of R. Okay. Okay, because this is infinite in length, yeah? So this is infinite, so your E1 by right should be equals to this, yeah? So remember, the E1 is a electric field intensity produced by the positive rho L to this particular point, which consists of a dq charge or dl element, yeah, on this negative rho L charge distribution, yeah. Okay, so we can just write this E1 to be equals to 0.5 micro, which is positive, over 2 pi epsilon naught, and R is a radial distance. So basically, it's clear that the distance between these two, the perpendicular distance between the two is equals to 2, right? So we have 2 here as a distance of R, and in the vector of R, which is in the vector from this positive rho L to a negative rho L should be equals to positive y. Yeah? So we know that the direction of R should be positive of y. So we can simply substitute it to be direction of positive y. Okay, so we have done the E field, which is produced by the charge positive rho L to the point of dl or dq. Okay, so once we have this, we can further use it to find the force on this particular dl element or dq element, yeah? On this dl or dq element, in which we can see that since we are dealing with a small amount of charge dq, so we can write that a small amount of force which will be produced to a dq element, to this dq element can be further returned to be equals to df, sorry for that, yeah. Okay, df shall be equals to dq multiplying with the E1. Okay, I repeat again. This df basically is amount of force which is produced by the E1, yeah, which is the E field intensity E1 towards the charge of dq. dq is a charge on this dl element. Yeah, so that should be the df. Yeah, right. So we can further write that the dq based on this will be equal to rho L dx, or we can just write rho L to be negative 0.5 micro, and the dx should be there, and the E1 is based on what we have obtained here, which is 0.5 micro over 4 pi epsilon naught in direction of positive y, sorry, yeah, positive y direction. Why we have this sign here? That should be positive, yeah, not negative, yeah, supposedly, right? Yeah. So from here, we can bring this particular dx to the left-hand side, in which will results on. So I need to bring it here, upward. So we're going to have the force df per unit length of dx. So that will give us negative 0.5 micro squared divided by 4 pi epsilon naught direction of y in the units of Newton per meter. Okay, so that should be our answer, which is the force per unit length as stated here. Okay, So that should be the answer for this question number 1, part A. All right. So do you have any question for this method of solution? Okay, yeah, hopefully all of you understand the method of solution. Let us proceed with part B of the solution of the questions here. Find the magnitude of electric field, which is 4 meter, directly below one of the wires. Okay, so let us use another color. I'm using a green color to, right. So we have a 4 meters directly below one of the wires. Let's say we assume that the point is here. The point is here, yeah? In which the distance between this particular line, sorry, let me correct my way of writing. Okay, sorry, I think I made a mistake here. Need to choose another point just to avoid any misunderstanding, yeah? Okay, your point should be here, yeah? Your point should be here. This is your line, negative 0.5 with 8 meter height, yeah? So your 4 meters should be here. Let's see, we assume the 4 meters is here. So I can write that this is my 4 meters distance, yeah, 4 meters distance. So yeah, please don't get confused with the red line here. The red line is your axis, yeah? So that's why this is very important to have different colors, yeah? So red line is your axis. So 4 meters is a point which is directly below the line charge of negative 0.5 microcoulomb per meter. Okay, yeah. So hopefully you understand what is the location of your point of interest. This is here, which is directly below the line. Yeah. So let us proceed with the next slide, just to ensure that you, yeah, I need to resketch it again for you. Okay. Sorry. Okay. So that's your line. This is your 0.5 positive microcoulomb per meter. And then this is your negative 0.5 microcoulomb per meter, right? Your point of interest just now is down here. Yeah, it's down here, yeah, which is a 4 meters. Okay, that's 4 meters from this negative 0.5 microcoulomb per meter, yeah, directly below, yeah, which is we can see that this is perpendicular, yeah, perpendicular, which is directly below the negative 0.5 microcoulomb per meter. So our interest is to find what is the electric field magnitude here at this particular position. That should be our interest, yeah. Okay, so before we can find the total electric field magnitude, we need to find the actual electric field intensity E vector. Yeah? So from the E vector, then only we can find the magnitude. Okay, so from here, we can see that the electric field at this particular location, okay, I can just write it here as E2, for instance. Yeah, the E2 shall be a contribution from two electric field. The first one is due to the positive rho L, so I just put it as EA. Yeah, EA is due to this line charge here. That's I just put it as A, and this is as B. And then we have the E field due to the line charge located at, the line charge of the label as B. Yeah, okay. So for the B, I think should be no problem. Yeah, because for the E field due to the line charge B, yeah, we're going to have it. So I proceed with the EB first. Yeah, so that should be rho L, which is over 2 pi epsilon naught R direction of R. Okay, and also for the EA, we're going to have the same equation because both are infinite in length. Okay, direction of R still, but there should be some differences in terms of the R, yeah, in terms of vector for both EA and EB. Okay, let us proceed with the EB first. For the EB, yeah, I go for the EB. Yeah, so let us have this as EB. Okay, so the rho L should be negative 0.5. Yeah, negative 0.5 microcoulomb per meter divided by 2 pi epsilon naught. R is a distance from this negative rho L to the point of interest, and as we have seen before, the perpendicular distance should be equals to 4. So we have 4 here, yeah? And how about unit vector of R? So obviously, we can see that the direction from this line charge to this point should be having R as equals to negative of Z direction. So that's why we have here should be negative Z direction, yeah, for the electric field direction for the EB. Okay, about the EA, so I'm going to use here, the EA. Yeah? So the EA is due to a positive line charge. So basically, we can then project that radial distance from this line charge to the point of interest here. Okay, that should be your radial distance, yeah? Yeah, radial distance from line charge to the point of interest down here. Okay, so your EA, what we have here, should be rho L over 2 pi epsilon naught R direction of R, and rho L should be positive charge of 0.5 microcoulomb per meter divided by 2 pi epsilon naught of R. So R need to be obtained, where R is the distance from this line charge to the point of interest. So in order to find the R, we have to first obtain the vector, yeah? Obtain the vector or use the hypotenuse method or Pythagoras method to find the distance of R. So since this is 4 and this is 2, sorry, it's not up to the scale, yeah? Which is 2, 2 is longer than 4, sorry for that. Yeah, 2 here and we have 4 there. So we can simply find that this hypotenuse or the distance of R shall be equals to set of 2 squared plus 4 squared based on Pythagoras theorem, and you're going to have it as equals to 20. So that should be your perpendicular distance from this A line charge to the point of interest. So going to have this as set of 20, yeah, for the R. Whereas for unit vector of R, yeah, which is this unit vector in this direction. So you need to find a vector first in order to find this unit vector of R, in which this vector shall be equals to this vector plus this vector, yeah. So it can be said that if I label this as vector of R, so the vector of R shall be equals to 2 in the direction of positive Y, yeah, 2 direction of Y. So remember, this is Y, this is X, and this is Z, yeah. So that should be Y direction, and down here should be negative Z direction. So we're going to have plus 4 direction of negative Z. That's how you obtain the vector of R. And from here, we can find that the vector of R should be equal to vector R over the magnitude of R, which will be 2y plus 4 of negative Z divided by set of 20. So that's how you obtain the unit vector of R. So substitute this into the equations here. So you're going to have 2 of y minus 4 of Z divided by set of 20. And subsequently, you're going to have that the EA shall be equals to 0.5 micro divided by 40 pi epsilon naught, and you're going to have 2y minus 4 of Z. So that should be your EA, yeah, which is the electric field produced by the positive line charge of positive 0.5 microcoulomb per meter to the point here. Okay, so we wish to find the EA and EB. Okay, good. So you just add them together. So that's how you obtain the total electric field at this particular point of interest. And from this vector of EA and EB, or the total electric field that you have obtained due to the summation of EA and EB, you can straight away find the magnitude. Yeah. So the magnitude is just based on the vectors magnitude that we have done previously. Okay. Is that understood on this example? You have any question on this solution? No? Okay. There's no question. I think you have understood it very well. Very good. So let us proceed with the next part. Okay. In part C, we have a thunderstorm, which caused a charge build-up on the surface of the Earth with infinite uniform surface charge density of rho s 49 coulomb per meter squared, and equal but opposite surface charge density at the bottom layer of a thundercloud located 750 meters above ground. Okay, so now we have additional charge distribution. Previously, you only have 2 line charges of infinite length, but for part C, we have additional surface charges now, which is basically due to this thunderstorm effect, where we have 2 charges. The first one is on the ground, yeah, with a density of 40 nanocoulomb per meter squared. And another one is, yeah, we have two, yeah. The first one is here, positive, on the surface of the Earth. And another one is opposite surface charge, or negative 40 nanocoulomb per meter squared, located at 750 meter above ground. So 750 meter above ground, yeah. So the question is, find the magnitude of the accumulated electric field in the thunderstorm at the same location below the transmission line in question 2B. Okay, means that we need to find what should be the total electric field produced at the same location here, which is 4 meters below one of the wires. Okay, hopefully you understand the question. So it means that if you refer back to this question here, you need to find what should be the new electric field equation or new electric field magnitude or electrical intensity produced at this location, yeah, when we have additional two charges. The first one is surface charge located on the ground, yeah, on the ground. So we need to rub this one first. Okay, I need to erase this particular writing first. Sorry for that. Okay, the first one is your surface charge is located down here on the ground. The density is negative 40 nanocoulomb per meter squared. And we have another one which is located here, somehow at 750 meter above ground. And for this location, I mean for this particular surface charge, it is positive 40 nanocoulomb per meter squared. Okay, I think that there's no much thing to be worried here because we are dealing with the infinite area of surface charge. So apart from what we have obtained previously, I mean the total electric field that we have obtained previously, we need to add with these two effects. The first one is the E field from this particular surface charge, which is, let's say we write this as E3 of rho s over 2, sorry. Yeah, rho s over 2 epsilon naught normal direction. And then we have another one here, which is E4 equals to rho s over 2 epsilon naught normal direction. So the important things to be considered here is only the direction of normal linear vector for both E3 and E4. Yeah, in which it does not depend on the distance between the surface charge and the point of your interest. Yeah, you just need to know what are the normal linear vectors for both E3 and E4. Yeah, so once you have this E3 and E4, you can just sum these E fields together with what we have obtained previously. So that will be your total or new total electrical intensity. Yeah. So for this particular normal for E3, that should be direction of positive Z, and for this normal, it should be negative of Z. Okay, that's all for this example part C. Okay, so basically these particular examples that we did have considered all the elements that have been taught in chapter 2 in Coulomb's law. Yeah. So hopefully you understand these topics on Coulomb's law clearly. Yeah.
Right.
Yes.
May I know for the surface charge what formula we use?
For surface charge.
Ah.
For surface charge, this is the equation. Yeah, because we are dealing with the infinite area of surface charge. Yeah, infinite of surface charge. So we have to use this equation. Yeah.
Okay.
Okay. All right. Right. So that's the end of chapter 2. So this is summary of chapter 2 that I think we just need to recall these things that we have learned previously in chapter 2. Number 1, we have understand clearly the concept of charges. Yeah. We have point charge, we have line charge, we have surface charge, and we have volume charge. Yeah. So we have to understand this concept very hopefully very clearly. Yeah. Number 2, you have understand the concept of force, electric field, and also Coulomb's law. Yeah. So we have understand how the electric field and how the electric force can be calculated. Yeah, from the Coulomb's law method. And part C, sorry, this should be B just now. Yeah. Sorry for my typo. It should be B. For part C, you have been taught on how to apply the Coulomb's law in calculating the E field intensity, which is induced by a specific charge distribution, which include the rho L, line charge, and also the surface charge. Yeah? Okay, so that's all we have learned previously. So that should be the end of chapter 2, right? And I believe that you have understand well on this topic of Coulomb's law. Yeah. You have any question for this chapter 2 so far? No, yeah. So if there's no question, I think we can now proceed with uh, lecture number 6. Okay, so that should be lecture number 6, a new lecture, a new chapter. Okay, lecture number 6, we're going to start a discussion on chapter 3. Chapter 3, if we base on the quantity formation, these are the topics that will be learned in chapter 3. Basically, topics will be on the flux density and a divergence theorem. Yeah, flux density and a divergence theorem. This is the main topics, the main title of chapter 3. So the content in this chapter 3 will be as follows. The first one, we're going to introduce the students to the concept of flux and flux density. Yeah, two things here, the flux and flux density. Okay. Number 2, once you have understand the concept of flux and flux density, then I'm going to bring you further to understand the concept of Gauss law. Yeah, Gauss law, in which we're going to use the Gauss law in calculating the E field intensity E for a case of symmetric charge distribution. Okay, so before you can proceed with the Gauss law, you need to understand first the concept of flux and flux density. Yeah, so then we're going to proceed with the Gauss law, in which the Gauss law is the alternative method which can be used in calculating the E field intensity for the case of symmetric charge distribution. Yeah, and afterwards, this chapter 3 will be ended by introduction to the concept of divergence and divergence theorem. Okay, so that should be the main topics that will be learned in chapter 3. Yeah. Okay. Let us proceed with lecture 6, the actual lecture. So this will be the topics to be covered in lecture 6. Number 1, we are going to explain about the concept of flux, electric flux, and also the concept of electric flux density. And afterwards, we're going to we're going to learn about the Gauss law. Okay, the Gauss law. So you can refer to Sadiku at this particular page 134 to 143 for further for extensive reading. Yeah, if you want to understand further about the Gauss law, also on the flux and flux density concept. Yeah. Okay, so motivation for this lecture 6 is that we want the students to understand well on the concept of flux, the concept of flux density, and then we want the students to be able to apply the Gauss law in calculating the electric field intensity. Okay, so it's very straightforward. Yeah, that should be the motivation of lecture number 6. Okay, so that should be the objective, which is a relation or related to the motivations that we have seen previously. Number 1, we want the student to be able to understand the concept of flux and flux density. So that should be two concepts that need to be understood clearly. And afterwards, from the first concept on the flux and flux density, we want to use it to produce or formulate the Gauss law. Yeah, formulate the Gauss law on how the Gauss law is said to be produced. Yeah, and then we're going to use it in calculating the electric field intensity. Yeah, from this Gauss law understanding. Okay. Okay, good. So let us have a look at the concept of flux. So flux is defined, basically is defined to be a sketch field lines, yeah, a sketch field lines, yeah, the words here, sketch field lines. Or in other words, we can say that the electric flux is imaginary lines, yeah, imaginary lines, a line which cannot be seen, yeah, imaginary. And it is said to be pointed outwards from the electric charge. Okay, so this is somehow similar to what we have done, I mean, from what we have learned previously in the case of magnetic flux. Remember where we have a magnetic bar, yeah, the north and south pole. Somehow we can see a line, yeah, which is originated from the north to the south pole. Yeah, when we have some sort like a iron powder somehow, yeah, located in around this particular north and south pole. I mean, this magnetic bar, we're going to see a line. So the line cannot be seen, but we can see somehow a route of line from the north to south pole. So this is what we call as a magnetic flux. Yeah, magnetic flux, or we call as a magnetic line. So this will be learned later in lecture or chapter 8 or chapter 7, yeah, when we learn about the magnetic field. Yeah, but the concept is the concept of flux here is similar to the concept of electric flux line, in which the flux, electric flux basically is a line which are imaginary, they cannot be seen. Okay, and for the case of point charge, is said to be originated from the point charge and is pointed outwards from this particular point charge. So somehow we can see that the flux should be look like this. Yeah, the flux should be look like this. So this blue color line is the flux line. Yeah. Okay, so this particular flux is having a symbol of psi of E. Yeah, the psi of E, which is a symbol for the flux line. Okay, for magnetic flux, the symbol will be the psi of M lah, yeah, which is the magnetic flux line. Yeah. So I'm going to erase this because this will be learned later in chapter 7. But the purpose of sketching this is just for us to compare. Yeah, that this particular flux line of electric is somehow similar in terms of concept with the magnetic flux that we have seen or we have learned previously in physics. Yeah. Okay. So back to this electric flux. So we have a line or flux line which has a symbol of psi of E. Okay, and the psi of E or the flux basically is a scalar component. Yeah, it's a scalar component. And one thing to be remembered is that the flux or the line must be having the same direction as the electric field intensity E. Yeah. So in this particular case, since we have the charge of Q, positive charge, so we know that the E field should be in this direction from the equation of E, which is Q over 4 pi epsilon naught R squared direction of R, in the vector of R, in which the direction is positive or it must be pointed outward or away from the charge. So that's why the direction of your flux should be following the direction of the E field, which is pointing outward from the charge. Yeah, but if your charge is negative, so this E field will be negative direction. So the direction of the flux will be opposite, in which the direction of the flux will be inward. If your charge is negative. So it depends on the direction of the electric field intensity. Yeah, for the positive charge, the flux will be pointed outward, but if the charge is negative, the flux will be pointing inward, following the direction of the E field. Okay, so that should be the concept of flux line. Right. So another concept that needs to be understood is that the flux, the electric flux, should be having same magnitude of the charge Q. Yeah. For instance, if your point charge is having a 20 Coulomb charge magnitude, so your flux line that is produced by this particular 20 Coulomb point charge will also equals to 20 Coulomb of flux. Yeah, 20 Coulomb of flux. That's why the units of flux is similar to the unit of charge, which is Coulomb. Yeah. So I repeat again, the flux magnitude should be equal to the charge amount. For instance, if you have a charge Q of 20 Coulomb, so your flux amount will also be 20 Coulomb. And that's why the unit for the flux or electric flux is similar to the charge unit, which is Coulomb. Yeah. Okay. So this is a brief description or brief discussion about the flux and its relationship with the charge. Yeah. Okay. So similarly, if we are having another charge distribution, for instance, a line charge here and a surface charge here. So in order for us to know what should be the direction of the flux, simply we just need to know what should be the direction of the E field. Yeah, because as I mentioned previously, the direction of your flux must always follows the direction of the E field. So basically, knowing that for this particular electric field, or due to the infinite line charge, we know that the E field is equals to rho L over 2 pi epsilon of R, direction of R. So due to the radial direction of your E field, so your flux line will follow the direction of this E field, which is in radial direction. Yeah. And similarly, for the case of infinite area of surface charge, we have learned previously that E field is equals to rho s over 2 epsilon naught in normal direction. Yeah, so if your point is here, so your direction of flux should be in this direction, and if your point is down here, your direction of flux should be this direction. So that's why we have these as the direction of your flux line, yeah, which is according to the direction of the electric field intensity. Okay, then this is the concept of flux. Is there any question about the concept of flux? No? Okay, so let us proceed further. Okay, flux, if we base on the previous slide that we have learned, flux basically is a scalar component, yeah, scalar component. But in EMT, as what I've mentioned before, we prefer to use a scalar, we prefer to use a vector quantity, yeah, vector quantity instead of scalar, yeah. So that is why we introduce another parameters which is called as flux density, yeah, or electric flux density, which is a representation of a flux in a vector form, yeah, representation of a flux in a vector form. Okay, so the symbol for the flux density is a vector D, yeah, vector D is a symbol for the flux density, and the unit for the D is a coulombs per meter squared. So from this equation, I mean from this unit, we can then say that relationship between the D and the flux density and the flux itself, the psi of E, will be based on this equation, yeah, from this unit, yeah, where we have the magnitude of your flux density D, yeah, shall be equals to the flux amount divided by the area. Yeah, I repeat again. We know that from this unit of flux density D, coulombs per meter squared. So Coulomb is a unit of charge, or in other words, it's a unit of flux, yeah, unit of flux. So the flux density D can be related with the flux line or psi of E from this equation, where the flux density D is equals to the flux amount divided by the area. Yeah, flux amount divided by the area. So if you base on this diagram, where we have a surface here, in which the surface is given by the area of A. And somehow it is given that the total electric flux that passing through this particular surface is given by psi. So we can see that the amount of flux density D, the magnitude of the flux density D observed or calculated on this particular surface shall be given by the total flux passing through the area divided by this particular area. So that should be how we calculate the magnitude of the flux density D, which is the flux amount divided by the area. Yeah, the flux amount divided by the area. Okay, and in terms of the vector, yeah, this is the magnitude, yeah, the flux over the area. But in terms of the direction, yeah, in terms of the direction, we know that the direction of the flux will be depending on the direction of E field. Yeah, so as such, we can say that the direction of the flux density D will be similar to the direction of the E field. Okay, so this is what we need to understand. Yeah, the direction of the flux density must always similar to the direction of the electric field intensity E. Yeah, so there are two different things. Yeah, this is electric flux density. This is electric field intensity. Yeah, so two different things there. This is electric field intensity. Okay, so hopefully you can differentiate between these two parameters. Yeah, these two vectors. Yeah, this is a flux density D. This is field intensity E. Yeah. Okay, done with that. I hope you understand this clearly. Okay, let's have a look at this example to testify your understanding on the concept of flux, yeah, before we can proceed further with the Gauss Law derivation. Okay, we are given here a case of uniform line charge with a rho L of 3 millicoulomb per meter, yeah, 3 millicoulomb per meter, that is the density of line charge distribution, which is located along the x-axis. Right, so let us sketch the diagram for this particular line charge. This is your y-axis, That's your x-axis, and that is your z-axis. Yeah, so your line charge is located here. That's your line charge. It is rho L equals to 3 millicoulomb per meter. Yeah, that should be your charge density. Okay, lies along the x-axis. So this is infinite in length. Yeah, this is from negative infinite, extend from negative infinite to positive infinite. Yeah. The question is, determine the electric flux crosses a spherical surface centered at the origin with radius r equals to 3. Yeah? Determine the electric flux crosses a spherical surface centered at the origin with radius r equals to 3. Okay, means that we are having another structure. The structure is in terms of sphere, okay, a sphere, in which the sphere is said to be having a radius of r, which is equals to 3, and the sphere is centered at the origin. Okay, so that should be the center of a sphere, which is at the origin. Okay, and the radius of this particular sphere is equals to 3. So the question is, determine the flux crosses the spherical surface, or it can be said, determine the flux that passing through this particular spherical surface. Okay, so that's a question. Okay, then. So how to solve this question? The question asks about the total flux. The total flux crosses a spherical surface. Yeah? So we know that flux must always originated from the source of electric field. Or it can, in other words, the flux must always originated from the charge. Yeah, flux must always originated from the charge. So in this particular case, your only charge source, or your only electric field source, is this particular rho L. Yeah, this particular rho L. So we can say that in order for us to find the electric flux that crosses a spherical surface, or crosses this particular surface of sphere, we need to understand the concept of flux clearly. Yeah. So as what we have learned previously, the flux will be determined by the charge. Yeah, and the flux amount shall be equals to the charge. Am I right? Yeah, the flux amount must be equal to the charge. This is what we have learned in previous slides. Yeah, the flux must be equal to the charge. So in this particular case, we want to find what should be the amount of flux that passing through this particular sphere. Okay, so to answer this question, we need to know what should be the amount of charge that is contained inside this sphere. Because the amount of flux shall be equal to the charge. Yeah, must be equal to the charge. So we can obtain the total flux crosses the surface if we know the amount of charge consists, or the amount of charge confined inside this particular spherical surface. Yeah, confined inside this particular spherical surface. So that should be how we answer this question. So based on this, we know that the charge that is confined inside this particular surface shall be given by integrations of rho L dl, because your charge is a line charge. Yeah, and the range of integration for the dl must be from this point to this particular point, because this is the range where the charge is said to be confined. And based on this, knowing that the radius of the sphere is equals to 3, so your range of integration is positive 3. So you're going to have that the flux shall be equals to rho L, which is 3 milli integrated, or integration of dx, I believe, from negative 3 to positive 3, and we're going to have the value of 6 inside this integration times 3, which will give us 18 millicoulomb. So 18 millicoulomb by right is a charge which is confined inside the sphere, and this charge which is confined inside the sphere is similar to the flux that is said to be crossing the spherical surface. Okay then, do you understand this concept clearly on the flux and charge?
Doctor,
Okay,
may I know
so
what the limit of integration is negative 3 until 3?
Okay, because we want to find the charge inside the sphere, right? Charge inside the sphere. And given that the sphere is centered at the origin, radius of 3. Yeah, means that the position where the sphere is said to cross these particular axis of x should be at -3 and +3. So that's why we need to integrate from -3 to +3 because this is the point, this is the position where the charge is said to be confined within the sphere. Okay, I hope I've answered your questions clearly, yeah?
Okay.
Okay, thank you very much. Okay, let us proceed with the next example. Okay, we are given a 25 millicoulomb point charge which is located at the origin. Calculate the electric flux that is said to pass through a portion of the sphere of 20 centimeter bounded by theta from 0 to pi and phi from 0 to pi over 2. Okay, so let us sketch this diagram. Okay, we are given this particular case, all right? So allow me to use a red marker. Okay, so we have a 25 millicoulomb point charge here at this position, at the origin. Okay, 25 millicoulomb, yeah? That should be the point charge amount at the origin. We are given a portion of a sphere. So a portion of a sphere is a 20 centimeter radius bounded by theta from 0 to pi and phi from 0 to pi over 2. So I believe that you have understand clearly on the spherical coordinate system and you have understand the range for the theta and phi clearly from our discussion lecture 2 in the very first week of EMT. So basically we can sketch the portion of the sphere to be look like this. Okay, yeah. So that should be the portion of the sphere. Sorry for my very bad sketching, yeah. Sorry for that. Okay. Okay. So that should be how your structure, I mean your sphere is drawn. Yeah, it's drawn. In which I can say that this is somehow is about 1/4 of a full sphere. Yeah. Yeah, 1/4 of a full sphere because your theta is from 0 to pi. Yeah, that should be the theta range, which is theta is from 0 to pi, and phi is measured. This is x, yeah? This is y, this is z, and phi is measured from x axis. So that should be your phi direction. So theta is from 0 to pi, and phi is from 0 to pi over 2. That is why we can see that this particular portion of sphere is 1/4 of a full sphere. Yeah, 1/4 of a full sphere. So that's how your structure of this portion of sphere should looks like. Yeah, 1/4 of the full sphere. Okay, so the question is calculate the flux passing through this particular portion of sphere. Okay, so we know that the charge is 25 millicoulomb magnitude located at the origin, and we know that for a full sphere, the charge will be uniformly distributed. Yeah, the charge will be uniformly distributed throughout the spherical surface. And if you want to find out what should be the amount of flux that passing through this particular surface, yeah, let's say we want to find out the charge passing through this portion of sphere, yeah, 1/4 of a full sphere. Okay, this is your electric flux line. So we can see that the flux that should be that can be considered passing through this particular portion of sphere should be equals to 1/4 of your total charge of 25 millicoulomb, because we understand that the charge, a point charge, must be uniformly distributed, yeah, on this full spherical space, yeah, full spherical surface. But since we have 1/4 of it, yeah, 1/4 of a spherical surface, so our assumption is that the charge will be, I can say the flux will be distributed by 1/4, yeah, of the total flux lines. That is why we have the total flux that passing through this portion of sphere will be 1/4 of 25, which is about 6 point something in millicoulomb unit. So that should be your flux amount that passing through the portion of sphere here. Okay? Yeah? All right. And for part B of the question, part of the question where we want to find the flux that passing through the closed surface of 0.8 meter plus minus 0.5 meter. So allow me to erase this sketching first. Okay, so we are given here for this particular condition for part B, I have to re-sketch the same diagram. Okay, that's my Z. We have a closed surface of 0.8 meter radius R, Z is from negative to positive 0.5, in which we can see that somehow this is a cylindrical surface. Yeah? So the charge remain at at origin of 25 millicoulomb, 25 millicoulomb magnitude. Yeah, that should be the amount of charge location which is at origin. Yeah, and let us sketch the cylindrical surfaces, cylindrical surface. Yeah, so that's how your structure should looks like. Yeah, okay, that should be a 0.8 radius meter, and the height is from negative 0.5 meter to 0.5 meter. Sorry, yeah, it is the drawing is not up to the scale, but hopefully you can understand this clearly. Okay. Yeah, 0.5 meters. So that's how the sketching for your surface should looks like. Okay, the question is what should be the amount of flux passing through this particular closed surface? Okay, so in this particular case, we can see that your charge of 25 millicoulomb basically is contained fully, contained or fully contained by this particular surface. Well, it can be said that this particular point charge of 25 millicoulomb is said to be confined by this particular closed surface. So it can be said that the total flux that will leave this particular closed surface will be similar, the flux that leaving this particular closed surface will be similar to the charge that is enclosed or that is said to be confined by this particular surface charge. So it can be said now that the total electric flux shall be equal to the enclosed charge. Yeah, the enclosed charge by this particular closed surface structure. Yeah, because it can be said that if we base on this diagram, your 25 millicoulomb charge is located inside this closed surface. So that is why we can say that the amount of flux leaving or passing through the closed surface should be then equal to the charge that is confined or that is enclosed inside the closed surface. So the flux amount shall be equal to 25 millicoulomb. Okay, so that is the concept of flux. That I hope that you really understand this concept of flux, relationship with the charge, and also the concept of flux density. Any questions? This example? Yes, yes.
Just now for AY, we want to divide by 1/4. I'm not understand.
Okay, because for part A just now, your portion of a sphere is a 1/4. Okay, if you sketch this diagram or this surface clearly, this structure that this portion of sphere basically is 1/4 of a full sphere. Okay, imagine that you have a ball. Yeah, you cut the ball into 4 different sections or 4 similar sections. So you have 1/4 of it, right? 1/4 of it. So that is why your charge amount that passing through the surface is 1/4, because we assume that 25 millicoulomb point charge, the flux of it is distributed uniformly throughout the spherical surface. And since we have 1/4 of it, your point charge, the flux line will be divided by 4.
Okay.
Is that understood then?
Yes.
Okay. Yeah. Thank you for your question. Your name is Lau Jisheng, right?
No. My name is Wei Han.
Oh, okay. Oh, Wei Han. Sorry for that. Thank you, Wei Han, for your question. Yeah. Okay. Thank you for the questions. All right. Hopefully, all of you understand this concept clearly. Yeah. Okay. So once you understand this concept clearly, then only you can proceed with the Gauss law. Yeah, we can proceed the Gauss law. But before we can have the equation of Gauss law, we need to formulate it. Yeah, we need to understand the Gauss law clearly on how the Gauss law is said to be formulated. Yeah. Okay. So we need to start with the flux density concept, yeah, which is a continuation from our understanding in the previous slide, yeah. Okay, imagine that we again use a point charge as our reference. Assume that we have a point charge Q here. A point charge Q is said to be located somewhere inside this particular surface. Yeah, a sphere is said to be, yeah, having a radius of r. Okay, radius of r. A charge of Q is contained inside the sphere of having a radius of r. Okay, the charge is said to be located at the center of the sphere. Okay, if we say that, if it is the case, so from what we have learned previously, from the equation of magnitude of D equals to the flux amount, yeah, divided by the area. Okay, this is the equation that we have seen previously, yeah, the flux amount divided by the area. The flux density is given by the flux amount over the area. Okay, if we consider calculation of the flux density on this particular surface, on the surface of your sphere, yeah, surface of the sphere. So we know that on this particular sphere, which is having a radius of radius of r, the area for that particular sphere should be equals to 4 pi r squared. Am I right? Yeah, this should be the area of a sphere, yeah, which is 4 pi r squared. Yeah, that should be the area of a sphere. Okay, so we know that from what we have understand from previous example, this is a closed surface. Yeah, this is the closed surface. So the amount of flux that is said to leave this particular closed surface shall be equals to what? It shall be equals to the charge Q that is enclosed or that is confined inside the surface. In which you can write that the psi of E shall be then equals to Q. So from these two information, or from these two concepts, we can say that the flux density magnitude D shall be equals to Q divided by 4 pi r squared. Okay, yeah? So from this understanding, from this concept, we can then write that the flux density D equals to Q over 4 pi r squared. And as what we have learned previously, the direction for the D should be equals to the direction of the E field. Okay, and we can see that from here, the D in the D vector shall be equals to Q over 4 pi r squared direction of R in the units of coulombs per meter squared. So which is similar to what we have here in your slide. Yeah, so we have here D Q over 4 pi r squared direction of R. Yeah. Okay, so it means that at any point on this particular surface, yeah, on this particular surface, the flux density that can be measured, yeah, that can be measured on this particular point on the spherical surface D, or on this particular surface radius of R, the flux density D that can be measured or that can be calculated shall be equals to this equation, Q over 4 pi r squared direction of R. Okay then, yeah, so this is the equation of flux density D. And from our discussion in chapter 2 on Coulomb's law, we know that if the charge is Q and the distance from the charge Q to the point is R, so we can say that at this particular location, the electric field can be returned to be look like this. Am I right? Where the E field shall be equals to Q over 4 pi epsilon naught R squared direction of R. Am I right? So from here, we can write a relationship between the flux density D and also the electric field intensity E from these two equations, in which we can see that the D and E is interrelated or unrelated by these terms, where the D shall be equals to epsilon naught of the E field. So this is relationship between the flux density D and also the electric field E intensity. Okay, is there any question for this derivation? Okay, hopefully you understand, yeah, relationship between the D and E. Okay, so now we can start with the, we can proceed with the Gauss Law derivation. Okay. We have a small portion of a sphere, radius of r, yeah, which is given this diagram. Yeah, we have a charge q located at the center of a sphere, and we can see that from our previous discussion, from previous slide, there should be a flux density d that can be measured on this particular surface, where the d shall be equals to q over 4 pi r squared, the direction of r, yeah, coulombs per meter squared. So this is the flux density which is measured on the surface of your sphere. Okay, so if we see that there is a small area of ds on your surface, on your spherical surface, yeah, a small element of area on your spherical surface. Okay, ds here is located on the sphere surface, yeah, on the sphere surface. So we can see that the element of flux that passing through this ds, yeah, the small element of flux that passing through this ds, I can label this as d of psi e, yeah, d of psi e, which is a small amount of flux that passing through this element of ds can be calculated by using this equation, where the d psi e shall be equals to the vector d dot product with the ds, which is a dot product between two vectors, yeah, because this d psi e is a coulomb, unit of coulomb. D is in coulombs per meter squared unit, and the ds is in meter squared unit. So multiplication between the two will give us the amount of flux that passing through this ds element or ds surface in the units of coulomb. Okay, so hopefully you understand, yeah. How can we write this equation? The amount of flux that passing through the ds shall be given by a dot product between the vector d and also the vector ds, or surface vector of ds on this particular surface. Okay, so from this information, we can see that if this is amount of flux that passing through the ds area, we can then use this information to calculate the total flux that passing through the total area of your sphere, in which this shall be given by this equation, yeah, in which we need to integrate. We need to have a closed surface integration of the d psi e, yeah, because the d psi e is a flux amount leaving the ds. So to find the total flux leaving the whole structure or the whole spherical surface, we need to integrate the d psi e, and the integration must be a closed surface integration. Yeah, must be a closed surface integration, which is given by a circle, yeah, a circle on this particular integration, which meant a closed surface integration. Okay, understood, yeah? And as what we have learned previously from the concept of flux, the flux that leaving the surface or leaving this the closed surface shall be equals to the charge that is located inside the surface, yeah? This is from a concept previously, yeah? The flux leaving the surface is equals to the charge that is enclosed inside the surface. Okay, so from here, we can further write the equation to be the d psi e shall be based on this equation above, which is the d dot ds closed surface integration equals to the enclosed charge. So this is what we call as the Gauss law. Yeah? Based on the Gauss law, in which the formulation of this Gauss law is based on our understanding on the concept of flux and its relationship with the charge that we have learned earlier. Okay, so this is the Gauss law. Any question for the Gauss law? No? Okay, there's no question. Let us proceed with this Gauss law introduction. I mean, the description about the Gauss law. So the law was developed by a German mathematician, Mr. Gauss, in the early 19th century. The law states that the total electric flux passing through any closed imaginary surface and closing the charge q coulomb is equal to the q coulomb. Okay, yeah? So I repeat again. The total electric flux passing through any closed imaginary surface, okay, the word here, total electric flux passing through closed imaginary surface, and closing the charge Q Coulomb is equals to Q Coulomb. Okay, in other words, if I have to re-sketch it for you, if we have a charge Q here, yeah, a charge Q, we sketch a closed surface, yeah, a closed surface which is imaginary. Yeah, this is imaginary. A dotted line means that this is imaginary. So we can see that the flux leaving this closed imaginary surface, the flux leaving the closed imaginary surface shall be equal to the charge enclosed inside the surface. This is the Gauss law, yeah? And this flux amount is given by the left-hand side integration, which is the closed surface integration of d dot ds, which has been formulated, which has been proven from our slide from our previous slide, yeah? So the d dot ds, basically, this is equal to the total flux leaving the closed surface, and it shall be then equal to the enclosed charge. Okay, so we have understood the Gauss law, hopefully, but the question is, how can we apply the Gauss law in calculating the electric field intensity? Okay, so this is what we're going to do now. We're going to apply the Gauss law in calculating the electric field intensity. So how the Gauss law can be applied, yeah? Okay, so let us proceed now with finding the Gauss law due to a point charge structure, yeah, due to a point charge structure. Okay, so let's say we have this particular point charge Q. We have a point of R, I mean a point which is having a distance of R from this particular point charge. So from our discussion in Coulomb's law last time, you know that at this particular point at R, or at this particular point, at that particular point, the E field is equals to Q over 4 pi. Sorry, I think I got a problem with my tab here. Not sure what's the problem. Sorry for that. Okay. Okay, at that particular point, from our discussion in chapter 2, we have learned that the E field shall be given by Q over 4 pi epsilon naught of R squared, direction of R, yeah, in which the R is the distance from the point charge to the point of interest. But now we want to prove that the Gauss law can also be used, and it can also produce the same equation as Coulomb's law here. Okay, so how to use the Gauss law in calculating the electric field? Okay, so what we can do is that we need to do few steps, need to adopt few steps. The first step is draw a closed imaginary surface, yeah? Draw a closed imaginary surface with a radius of R enclosing the point charge Q. In other words, we need to draw a closed imaginary surface which will pass through the point of interest. Yeah, which will pass through the point of interest. So in this case, our point of interest is here. Yeah, so you need to draw a closed imaginary surface that passing through that particular point of interest. So your imaginary surface that can be applied here is a spherical surface. So why spherical surface? I'm going to explain to you later. Yeah, but for the time being, we just accept that the spherical surface can be applied. Okay, detail will be explained later. Don't worry. Yeah. Okay, so we have a closed surface which will be look like this. Oh, sorry, we have the diagram itself. Yeah? Sorry if I need to erase this to avoid any confusion. Okay, so that is your closed surface as sketched here. All right, so that's your closed surface. It's passing through the point of interest. That's your first step. Second step, we can then apply the Gauss law. Yeah, and from the Gauss law output, you must be then able to calculate the flux density. So how can we calculate the flux density from the Gauss law? Okay, then from the equation, yeah, when we have a closed surface integration of d dot ds equals to the enclosed charge. Okay, that's the equation of the Gauss law. Okay, so the left-hand side, yeah, left-hand side basically is the integration on the surface of your closed surface. Yeah, the left-hand side is the integration on the closed surface. Yeah, on the closed surface, whereas the enclosed charge is the charge that is said to be located inside your closed surface. Okay, I repeat again. The left-hand side from the Gauss Law equation is the flux leaving the spherical surface, in which the flux leaving the spherical surface is evaluated on this spherical surface itself. Yeah, that's why I put the arrow on the surface itself, on this arrow on the surface. Whereas the enclosed charge is the charge which is said to be located inside the Gaussian surface or the closed surface. Okay, I need to need to reword this imaginary surface. This is also called as a Gaussian surface. Yeah? Gaussian surface. Okay, Gaussian surface. Right. So back to our discussion here. Yeah, I hope you understand that left-hand side from the Gauss law should be evaluated on the surface of the Gaussian. Enclosed charge is a charge inside the Gaussian. Okay, let us go for the left-hand side first. For left-hand side, I do it here. Left-hand side, which is d dot ds. All right. So that will give us integration. Okay. Okay. What should be the direction of vector d? Okay. From what we have learned previously, okay, since we are using the spherical surface, yeah, spherical surface, the vector d can be in terms of dr, direction of r, d theta, direction of theta, and d phi, direction of phi. So we can have three distinct component of flux density d, yeah, because we are using the spherical systems of coordinate. But for the case of Gauss law, we can only take, or we can only choose one direction. Can only choose one direction. So in this particular case, we know that the charge is at the center of a sphere, a Q, a point charge. And we know that the point charge, the direction of the E field is always in the direction of radius of R. Yeah, radius of R. That should be the direction of the flux density or the direction of field intensity E. So as such, we can see that the direction of theta, direction of phi can be cancelled out. We can only have the direction of R in that particular case. Yeah, so that's why we have the vector of D shall be only consist of dr direction of R. Yeah, dr direction of R. Okay, due to this argument. Yeah, so the component of theta, the component of phi can be cancelled out. About the ds which is evaluated on this particular surface of a Gaussian. So we know that from our discussion in lecture 2 on the system of coordinate, your ds shall be equals to, the vector will be r squared sine theta dr theta d phi. Yeah, in the direction of r in the vector. Okay, that should be the ds that shall be used on that particular surface of sphere. So how can we obtain this? So please refer back to lecture 2. Yeah, if you got any problems, you can consult me later on. Yeah. So the ds here should be r squared. I have to rewrite for you sine theta dr d theta d phi direction of r. And since this is a dot product, so r dot r will be 1. So immediately, if we do the integration, we're going to have 4 pi r squared because we are dealing with the closed surface integration. Yeah, so for a closed surface integration, both theta and phi will be having a maximum range. Yeah, theta 0 to pi, phi from 0 to 2 pi, and up you're going to have the value for left hand side will be dr of 4 pi r squared. Yeah. Okay, then we're going to have it as dr, okay, of 4 pi r squared. And for the enclosed charge, which is the charge inside the Gaussian, we can notice that from this diagram, the enclosed charge by the Gaussian surface is only a point charge Q. So the enclosed charge here is only a single charge Q, which can be then returned to be just Q. That is the only charge that we have in this particular case. Yeah. So from here, we can write that your dr shall be equals to Q over 4 pi r squared. Yeah, and further on from our relationship just now, where the vector of D is only consists of dr of r, we can write that the vector of D shall be equals to dr of R. Sorry for this interruption. Yeah, dr of R. Okay, and then we can have it to be equals to Q over 4 pi R squared, the direction of R in coulombs per meter squared. Okay, so this vector of D basically is evaluated on the surface of your Gaussian, right? So, but what we have obtained here is only the D, right? The flux density D. The aim is what? The aim is obtain the field intensity A. So that's where the third step comes in, where the third step is just simply use relationship of D equals to epsilon of E, which can be used to find the field intensity. So as such, we can have from D equals to epsilon of E, we can have E shall be D over epsilon naught, which will be Q over 4 pi epsilon R squared, direction of R in volt per meter. So at any position, having a distance of R from the line charge, the E field can be returned to be looked like this, or can be calculated to be looked like this. Okay? Is that understood on the calculation or on the working principle of Gauss law? Okay, so what we did here is a steps, 3 steps need to be taken using the Gauss law for the case of point charge now. The first step is to draw the Gaussian surface or imaginary surface. Number 2 is to use the Gauss law straight away, and finally is to apply relationship between the D and the E vectors. Yeah. Okay. So I'm going to stop here because it's almost 12:32. Yeah. For next lecture on Tuesday, we're going to proceed with another method. Another charge distribution in which we're going to apply the Gauss law in calculating the electric field intensity due to a line charge distribution. Okay. All right. I'm going to end the class now. Before we end the class, we are going to have a first quiz for the semester. Yeah, let me stop the recording for this lecture.